I'm Mark Bouris, and this is Straight Talk.
You're trying to describe nothing less than the beginning of everything and its change and growth to now, and that demands imagination.
Professor Alan Duffy, now he's recognised around the world as a leading astronomer. His ability to simplify complicated scientific theories makes you want to lean in and be hungry for more. Can I go to something sort of what I think is sexy cool? Is dark matter. And now, he and a global team have created the deepest underground physics laboratory in the Southern Hemisphere, right here in Australia.
It's 5 times more of it than everything we can see put together. So there's this huge extra amount of our universe invisible to us, fundamentally invisible to us. And if we discover the nature of dark matter, we've explained more of the universe than all of human scientific endeavor. There's a brewing scandal, and I think it may well be one of the biggest scandals in modern scientific history.
Alan Duffy, welcome to Straight Talk.
Thanks for having me, Mark.
I denote an Irish accent there.
Yes, you do. Yes, I was.
What's the deal?
I was actually born in England. I will note that with a little bit of shame. But I come from an Irish family, and we were raised in Northern Ireland, Belfast for a little time, and then a little regional country town called Ballyclare. And just grew up in one of the most extraordinarily beautiful countries, but also at a time that was a little challenging, as known as the Troubles.
So you grew up during the Troubles?
Yeah, so in a period that was called in the 90s, it was called the tit for tat. So one evening you get the news and someone on one side had been hit. So the next night you knew the news would tell you the tit for tat would be the other side would get hit.
My mother, she was orange, and my father, he was green.
Ah, okay, very good.
No, I mean, that's a song.
Okay,
but my mother's Irish, so
yep.
yeah, it's but from the Republic, but
yep.
As opposed to Northern Ireland, which is a lot different. So, with the area you come from, the village you come from, it sounds like a village, a town, on the coast.
Pretty close. There's nowhere in Northern Ireland. It's not
but it's not inland though. But so more the west coast side, or towards the west coast, or the east coast of Ireland. If you're going down the top of Ireland. Yeah.
So it's definitely so County Antrim, so absolute east coast. So we would have some of those iconic features. That side of the country are things like the Giant's Causeway. So there's a connection between Ireland and Scotland, known as the Giant's Causeway.
Allegedly.
Where lava has poured in. And if no one's seen this, it is an absolutely extraordinary sight. But lava has poured in across that area, and then has cracked into these gigantic columns, hexagonal columns. It is the most surreal looking landscape. And the idea was there was a giant who built a land bridge between a Scottish giant called Benadonner, who was going to come over and take out the Irish giant Finn. And the Irish hero in this story, and this is partly, I think, quite a revealing story about Irish nature, but Finn wins, but he wins by his wife's smarts in out-tricking the Scottish giant by, essentially dressing up as a baby and saying, well, look at the baby of Finn, the giant. If
Can you imagine how big the dad is?
Yeah, and eventually that's the idea. So I kind of love that our battle of giants is won by smarts and dressing up as a baby and having your wife figure it out. I think that's quite a revealing statement about Irish character.
Actually, what's interesting about that, or just talking to you, is that Irish love a story. I haven't spent any time in Northern Ireland, but I have certainly in the Republic. And if you go over to Galway, a place like that, they still have storytellers there. Especially in the pubs.
Yep.
Along the west coast, east coast is slightly different, but and it's all about fables and, fairies in the garden and all these fantastic stories. And if you go right back to the, Homer, et cetera, the same thing, stories, fables, but really about the human experience. And then here we have sitting in front of me, or you sitting in front of me, are a scientist at an absurd level in astrophysics, as opposed to, just a scientist, not a biologist or something. There was nothing wrong with biology, by the way. But
I was about to say, I think they do a more impressive job than I do, but okay, keep going.
No, but in terms of, the more difficult lane of science, like physics, that's where you sort of swim. And it's sort of a lot of logic involved, but at the same time, a lot of imagination involved, because pretty much everything you guys deal with is in theory, it's theoretical.
Yep. You can't have it in your hands.
It's theoretical. And yet at the same time, on the flip side of it, here you are, an Irish boy who's just told me a story about the giant fin and the giant steps that allegedly go across from Scotland from Northern Ireland. How do you reconcile those two things? I mean, are they, because I would never expect to sound, I'm being very judgmental, but to get an Irishman who loves that type of stuff, who just told me that story, to end up being an astrophysicist.
Yeah. So I think there's an idea of a preconception that if you're in science, you're interested in science, that you must be some sort of cold, analytic kind of a character. And in my experience, the astronomers in particular, astrophysicists in particular, tend to be incredibly creative people. So we are very much, I think, struck by the beauty of the science that we do. And these images you get from these telescopes are truly stunningly beautiful. So I think we're very fortunate in our science that it is visually beautiful, that the ideas that we're exploring, and with some creativity to join the dots, so to speak, but you're trying to describe nothing less than the beginning of everything and its change and growth to now, to see all of the wonder and the magnificence of the galaxies and the stars and the nature of the planets as they formed around the stars. You are seeking to describe nothing less than everything. And that demands imagination and creativity. You can't just do it by pure maths alone. You must have that physical insight. You must have a detailed picture in mind. And your brain allows you to make sometimes those leaps. And I think that creativity is not just helpful, it's critical in doing science.
So that's quite interesting. So just in context then, there have been many famous physicists. Of course, we all know the famous names like Einstein, etc. But there's even more famous ones than Einstein, which most people don't know, but doesn't matter. In physics, I'm talking about.
Yeah.
But
don't worry, he was pretty good.
Yeah, but he was good. But there's people who've succeeded him who are equally famous but never get talked about. But one of the things I notice about these individuals is that they do have a great imagination. They have this great imagination. And to some extent, to have a good imagination, you've got to be fairly fearless. You can't be fearful. You've got to be fearless because, fear steals your imagination. So you've got to have this great imagination. And then they run off and they prove their theory. It doesn't prove anything exists, but it prove their theory through mathematics.
Yeah,
the use of mathematics. If you go right back to the concept of quintessence or dark matter or light
right,
versus light, you can go right back to Aristotle, who was not dissimilar to your fable writers. I don't know who wrote that fable about Finn, but right back, he was an imaginary person, and he took the view that quintessence. He didn't call it quintessence, call it something else. He called it ether, actually. Yeah. But he said it was the fifth element. It only existed up in the cosmology, up there in the stars somewhere. Had no idea what you understand about quintessence or what it actually is in terms of a form of dark matter.
Yep.
He was a great imaginer. Newton, a person with a great imagination. But they all then went and put mathematics around it to actually prove their imagination. What I want to ask you is, and if we take this right back to the beginning of so-called beginning of time, the theory of the Big Bang, or whatever the new theories are that have evolved around it, or refined theories, are they all bullshit? Bit like Finn's story. There's no mathematics around Finn, but maybe because we've got the steps there. But is it all bullshit, or is it theory for theory's sake, but and mathematically proven? What's the point of it all?
Using your imagination. Let's start with that. And I love that some of the names you suggested. The key point is you have a coherent, incredibly detailed picture in your mind of the scenario that you're trying to explore or explain. And then you're right. Then you are ruthless with the application of the mathematics and daring in where you let it take you. And in fact, Einstein, his greatest blunder, as he named it, was his equations predicted that the galaxies, as we saw them all around us, their gravity would let them fall together or they would have to move apart. They couldn't just hang in isolation that's unstable. But all the astronomers at the time told him, no, it's eternal universe. That's what they do. They stay there. So great was his genius. He was actually able to come up with a way to just about fudge the answer in his theory. And then a new astronomer came along, Edwin Hubble. He showed the universe is expanding, all the galaxies moving away. Einstein realized, well, I should have predicted. I should have been that bit more daring in that prediction. And, damn the astronomers and their, misidentification at that point of those galaxies. So even Einstein was sometimes afraid to take that next step. But in the same way that we have the application of the mathematics and the rigor to your concept, to your creative picture, I think that last bit is sometimes missed by a lot of people who think it's just about having an idea. It's about having an idea, and then, as Einstein did, put 17 years of hard work in to make the mathematics and the predictions rigorous enough.
Along with some help.
Yeah, and he wasn't alone. That's right. I mean, he
wasn't a great mathematician. I mean, he's a great mathematician. Wasn't the greatest mathematician of the time.
No, absolutely not. No. He was obviously pretty good, but he even said the greatest mathematician, or one of them at the time, was Emmy Noether. So there's she was a mathematician. She came up with, was often described as one of the most beautiful theories, Noether's theorem. For whatever reason, she's just not famous at all. But even Einstein considered her the genius of the time. Now, the whole point of those kinds of predictions and is it all bullshit? And then you look back to to the Big Bang and all the other theories. There's a lot of theories get spouted.
Yeah.
And if I'm honest, I don't have a good sense for how rigorous the definition or the derivation of that theory has been, or how real even the scientists are about thinking it's going to get tested. But so long as you've come up with a way to test your theory, that's science. Will I personally be spending my time in the week trying to disprove this theory? Well, probably not. I mean, most theories you can take a quick sniff test at, and it just doesn't look right. So in theory, everything gets tested. In practice, only the more compelling theories do.
Is science today more about proving ideas or even dreams, or is it more about disproving what is upheld as the conventional thinking?
Yeah, right. Okay, so this really does speak to the nature of the scientists who do the work of science. If you could disprove Einstein, Nobel Prize, straight away. It doesn't get any bigger or better than that. So everyone is motivated to find holes in these accepted theories. The fact that for now 60 plus years, it's just passed every hurdle is actually a source of frustration for us in the community. We know it's incomplete. We know it doesn't describe everything in the universe, but we can't yet figure out where to take the theory beyond that. In theory, you only ever disprove a theory. You can never be 100% certain that it's right. You always know it's incomplete at some level. So, but there's just a limited amount of time in the day. So you're not always going to start from first principles to reprove everything, redrive it. You just have to trust that your colleagues, the peer review system, the fact that everyone else is checking it, that gives you a certain level of confidence to have a starting place that's a little further along, and then you could advance things. So in that way, we have a complex ecosystem where there are checks occurring. People are constantly trying to pick holes in each other's predictions theories. And all the while, there is a balance between this incredible natural collegiality in science, but quite an aggressive competitiveness as well. If you're on the frontier of science, it is tantalizingly, it's actually almost a visceral experience of knowing that you are seeing something that no one else has ever seen before. That's an addiction. That is an incredible attraction to the field.
It's what drives them.
That's right. You're exploring the unknown. So
it also kills them with frustration.
Oh, well, I mean, you got to pace yourself too. And I think that the fields, there's certainly been instances where burnout is real. I think modern science is suffering from a different style of burnout to the decades before. The working environment has become far more challenging, I think, today than it ever has been. But at least in principle, if you can retain the passion and the excitement, but still pace oneself, then you can get to those frontiers and you can really start to explore something perhaps no one has ever seen before. And that is an exhilarating kind of experience.
So where in space do you specialize?
Okay, so my day job is creating universes on supercomputers, so little baby universes, and throwing in everything that we think it takes to make a galaxy like our own Milky Way, and then pressing go and seeing over the course of 13.5 billion years, obviously somewhat sped up on the supercomputer, do I get a galaxy out that looks like our own? And if not, why not? So in that way, I use it like a numerical laboratory. I can change the inputs. I can tweak the laws or the recipes, as it were, for how perhaps stars form. All of these kinds of things that we accept in astronomy, but different to other science. We can't go out and run the experiment again. We can't have a galaxy collide in a different way, but the computer allows us at least that flexibility.
Well, the modeling on the computer, I guess.
The modeling, yeah.
So what type of environment, like a university environment, or I mean, like who's paying for the supercomputers for a start? Like,
oh yeah, okay. So this is Swinburne, yeah. So my uni Swinburne has a supercomputer.
Okay, Swinburne. Okay, so Swinburne, like especially these days, has like really emerged as a great institution. Like,
huge tech hub. Yeah.
It wasn't so much a few years ago, but for some reason, like maybe a couple of years pre-COVID, it just came through aggressively. So they fund the supercomputers because they're not inexpensive. They're quite expensive.
Yeah.
Unless you want to cobble one together yourself, which you probably could. I presume you have a number of PhD students who you are supervising, who are, the process is you tend to, whilst they're doing their PhD on whatever it is, you tend to have access to these individuals and they help you out big time.
Absolutely.
And what you're trying to do all the time, I presume, is, the PhD students, is get stuff published. Because, apart from for a PhD student, generally speaking, they've got to have publications in order to get their PhD awarded to them.
That's right.
Candidates. But where do you want to publish your stuff?
Yeah, look, I mean, Nature is still considered
for you guys as well.
Oh yeah.
Okay,
so there's a little specialty version called Nature Astronomy as well.
Okay, Nature Astronomy. Okay, so what's interesting, because I'm leading to something here. What's interesting about that is that you get reviewed,
by
your peers.
Yeah, pretty brutally sometimes. Yeah.
Well, most times.
Yeah, if I'm honest. Yeah,
they're trying to pull it apart, right?
That's right. Yeah.
And it's very frustrating as a scientist. From your point, it's very frustrating. But your peers then say, this is pretty robust. We like this. They've reviewed it and it's been back and forth. And the editor says, yeah, we're going to publish it. And all of a sudden you publish something and everyone reads it and they go, wow, how good is Alan? This is unbelievable. And his team, and there's about 50 people sitting on the publication. And maybe you're the first or the last. I don't know where you sit. But
no, I put myself last. Don't worry.
Yeah. Okay. So, but all of a sudden this becomes embedded.
Yes.
How do I know if it's real or not real? Like, I got no fucking idea. Like, by the way, I think what the whole science community does, particularly in Australia, is brilliant. Okay, I mean, I have the greatest respect for them, but also there is some shitty stuff that gets done. Not so much in Australia, but stuff where some of the findings have been.
Oh yeah, mistakes happen, big mistakes.
How do we know the veracity?
Yeah, it's trust. I mean, fundamentally, there's the principle of science is that you, in principle, should be able to go right back to the very starting point. And there's a logical sequence, and there's the data, and here's the analysis tools, and I can reproduce that. And then I can connect to the next piece, and there's a logical chain. In practice, there's every morning in astronomy alone, there will be somewhere in the region of 100 to 200 new papers every morning around the world. And it's on something called Archive. So no one is reading all of those, let alone trying to recreate those. So even within our system, as you said, there's peer review. So we do take that as the first step in the trust. The second step is that you don't trust completely. And certainly when something begins to, sooner or later, it will be found out if it's wrong. It's unfortunate, in particular if it's in medicine, because there can be real world
massive consequences. Totally.
And in fact, there's perhaps something coming up about Alzheimer's at this point that there might be a bit
about the amyloids.
Absolutely. I don't know anything about it, but I just saw.
Please don't tell me, because I know doctors who test people on this stuff for that marker.
Yeah.
and treat the individuals, or test you for the marker, which is a side discussion, and you don't have the marker, but all of a sudden they get Alzheimer's, which turns into dementia, and that's terrible. I mean, I hope it's not right. I really hope it's not right. The allegation, so-called.
Yeah, so there's a brewing scandal, and I think it may well be one of the biggest scandals in modern scientific history. Yeah, so it's around the Alzheimer's.
I mean, you guys will be all talking about this sort of stuff. Does this get talked about in the hallways?
Oh yeah, because
did you read that?
Yeah, well, this is front cover Nature, so we're aware of it. We don't know the science of it, right? We're astronomers. What do we know about medicine? But we can see what looks like fraudulent behavior. We can see where there's been issues creeping up. So, and that strikes, and the danger is not just the direct, and in this particular instance, the scale is so large that it could be, talking potentially millions of people have been affected here. So it really doesn't get any worse than that. But just in general, this then impacts the credibility of all sciences, because we're all using the same self-correcting approach.
Because this is all peer group reviewed.
That's right.
And it was published by Nature.
Yeah, and the highest level, absolutely highest level. So what we're finding now is, as if we needed that reminder, we do need to go and check. We do need to incentivize scientists to go back and check these works. Now, eventually, if this is the fraudulent allegations are upheld, well, science did correct, right? It took a depressingly long amount of time for that instance.
Yeah.
But the fake was uncovered.
That makes sense. So
we do get there.
That's comforting.
We do get there, but it's not a perfect system, but what worries me is that we are in an ever increasing race to produce publications. There are literal universities or research organizations that are essentially called paper mills, where all they do just churn papers, limited value, perhaps not even any value associated with them, just to be able to say, I've published 40 papers this year. And that, how are you publishing 40 papers? You're kidding me, right? Like I don't barely have time to read 40 papers in a year, let alone write and do original research. And so there's clear challenges in the system. Everyone knows it. We don't have the solution for it.
It's funny, as you were speaking there, I was thinking about the area of academia that I'm involved in, and that is economics and economies and stuff like that. Like there is a sort of a science around that, not the same science that you do, but it's mathematically based.
No, actually, I wrote a paper called "The Economics of Galaxy Formation," of First Galaxy Formation. So we may get to that. We're pretty close, I think, on that.
But it is statistically based. So, we're all using the same sort of statistical tools and methodologies, et cetera, within reason. It's funny, we always, when we look at the economy now, when we looked at the economy during the GFC period, we went right back to theories that were espoused by people like Keynes, John Maynard Keynes, and we started using those theories globally around the world. But all of a sudden, we realized, 30 years ago that the Keynes theory didn't work, and they went to the Friedman theory. And then they realized the Friedman theory wouldn't work, and we've gone back to the Keynes theory post-GFC. Now they're realizing the Keynes theory has overdone things, overcooked things. Now we've got this inflation. Now we're going back to the old theories. So we tend to go back to where we started from, notwithstanding there's all these new theories in the science of economics. Is that the same thing in the science of science? I mean, particularly in astronomy, do you find that we have a new theory, but hang on, we've overcooked it, we've overreached, and we've got to peel back?
I guess from our point of view, the main difference is in astronomy, whatever theory that we are using is not impacting the galaxies and the behavior around us. Right, so the system isn't responding to the theory in that way. So in other words, because you've adopted a Keynesian approach, your economic models have done X, that's led to Y happening in the real world, and it can, it has overcooked.
Because it's a legitimate test.
Yeah, well, but you've also influenced the actual system you're supposed to be predicting, right? So the system is responding, knowing, this is a Keynesian moment. Well, now I know how the investment from government's going to go. So you're going to get private equity responding, and so you're going to. The galaxy I'm observing does not know that I'm observing it, right? So it's not going to change its influence, which is why I think scientific fields that deal with people, both sociology, economics, the problem is the person knows that you're trying to test them.
Yeah.
And they know what your theory is, perhaps even.
And the behavioral
and they're changing. Yeah. And so it's going to stuff up your experiment. So I think it's a much, much harder problem in economics. I also think that there's a challenge where we've got where we are data rich and insight poor. And economics is, I think, one of the places where that's perhaps most painfully pronounced, where the vast amounts of information we have, everything we can measure, leads us perhaps overestimate how much we understand. And we're
basically confused.
Yeah, and we can pick out whatever correlations we want to see. Yeah. And it worries me that, again, there's a lot of faith being placed in theories, and we want to have guidance, but I think common sense must also be weighed in there as well. And what that means in astronomy, we are practical people as well. So we will have Einstein's general relativity. We know that describes gravity on the largest scales, at least to the level that we can test. But if I want to launch a rocket, I'm not solving Einstein's GR. I'm using Newton's 350, 400-year-old theory because I can do it in one line of calculation, and the answer is pretty much close enough. So it's fine. So in other words, even though you can have this hugely powerful predictive theory, you can still take shortcuts. And we're just, again, very practical people. So we just want the answer that's good enough.
Can I go to something sort of what I think is sexy cool about your area of study is dark matter.
Yeah.
So we don't know what dark matter is. You know what it is. You have a theory about it, but we don't really know what we're describing. But somehow you're all convinced it exists.
Yeah.
And yet no one can see it, measure it, nothing. Is that correct? But it's out there. It's everything else that we can't sort of see nearly.
Yeah.
Is that right?
So yes. So that in my simulation, one of the ingredients is a new kind of matter. So something with gravity, but that is fundamentally invisible, doesn't shine or absorb light, can't see it, can't touch it, smell, taste it. It can travel through solid walls as a result. It can travel through the entire Earth without colliding. It is a ghost. So one of the key ingredients is this dark matter. And it's not a little bit. It's 5 times more of it than everything we can see put together. So there's this huge extra amount of our universe invisible to us, fundamentally invisible to us. And yet without its gravity, our galaxy would not have formed. We would not be here were it not for this unseen companion to our galaxy, to our lives. And in fact, it's in this room right now. It's flying through us like a ghostly wind, which all sounds crazy. Why can I be so confident to say, why have I dedicated 10 years of my professional life to try to find the nature of this dark matter? And it's because we can see the motion of the stars and gas pulled by the gravity of an unseen companion. So we can literally see them move around. Now, there's an analogy I like to use with that of the wind. Even though we can't see the air, we know it's there because we can see its actions on trees as it blows in that wind. In just the same way, we've got those things that we can see, those gas and stars moving around by that dark matter gravity. And if you cast your mind back a couple hundred years, we actually didn't know what the air was made of at all. So scientists at the time knew it was there. They could see its effects of the wind, didn't know what it was made of, didn't know what atoms were. That's where we're at with dark matter. We know it's there. You can see its effects on the stuff that we can see of the galaxies, but we don't know what it is made of. A new kind of particle, something more exotic. We don't know. But we just know there's a lot of it out there. And if we discover the nature of dark matter, we've explained more of the universe than all of human scientific endeavor to that point. It's a tantalizing prize. That's why we're part of the hunt.
We tantalized about it because our nature is that we tend to put everything into a compartment. We think we know what an atom is, but all the other stuff that sits within an atom, beyond electrons, etc., like that, all the other new particles that are being discovered all the time. We sort of put a name on it, and we sort of can imagine it, if you know what I mean. But dark matter, we got a name for it, but we don't really have it broken down like an atom is. Locally, there's, an atom. They teach you that they put words. There's a nucleus, and there's protons and neutrons, and there's electrons, and there's other things now. So as soon as you put a name on it, I can compartmentalize it, and I can sort of imagine it.
Yeah.
Right. Is that because you guys haven't yet, or maybe have you put names on parts of dark matter? Or are you saying, look, this is so exotic, we can't give it a name because we don't know what it is yet?
Well, I'll give you a couple of proposed candidates.
Yep.
Some are more conceptually, I think, straightforward than others, but there's no shortage of suggestions, because if by chance you happen to be right as a scientist with that predicted particle, bang, Nobel Prize, right? So everyone's, why not have a crack? Just come up with a particle.
Yeah.
It's not quite as easy as that, but it's also not too much more difficult. So the kind of particle that I look for, the kind of dark matter that I look for, and there's an experiment I'm a part of. It's led by Professor Elisabetta Barberio of UniMelb. It's known as SABRE. This is looking for dark matter that's, about the atomic size of, a few times that of the proton. So something like, sodium, or just a standard kind of atom size, right? So, and then really there is just a particle with a weight that's not too dissimilar to an atom.
I just need to understand this. So you're saying that there may be a particle that is similar in sodium in terms of its weight, and that is, where it sits on the
periodic table,
table.
23 atomic mass units,
whatever,
right? But something like that. Yeah.
Basically, you're saying how many electrons it's got, but you're saying that there's something of that sort, because that's pretty big. That's not small. That's
it's not small, but that's the middle of the range, right? And so if we think of something that's the easiest one for me to conceptually get, because it sort of feels a little bit like an atom, but
right.
But doesn't interact with
feels. That's an interesting word for you to use.
Yeah, well, you're trying to picture it. You're trying to sort of
yeah.
But if this idea is correct, then right now you and I have a wind of those particles traveling through us. And in fact, I'll just take a quick step back. So the idea of the dark matter is that it sits not just out there in the cosmos, but our galaxy actually is sitting within a vast cloud of this dark matter. So it is all around us right now. Our sun is traveling around the Milky Way. It takes about 250 million years to do a lap. An incredible speeds, 240 kilometers a second, give or take. But it's a big galaxy. It takes a long time. So it means that our sun is traveling through this cloud of dark matter. Now, if you're in a car, as by analogy, on the stillest of days, there's no air, no wind at all, air is completely still, and you start to drive and you put your hand out the window, you're going to feel the rush of the air against you, right? That's you traveling through it. You call that a headwind. And in just the same way, our sun is traveling through dark matter. It's minding its own business. But because it's traveling through that cloud of dark matter, it's going to look like the dark matter is rushing towards us, just like the air did in the car. And in that instance, I know then exactly from where the dark matter wind is coming. I know how fast it's blowing. And if I assume this particular WIMP candidate, I then know how many particles on average are passing through each of us every second. And it's about, basically in your size of your eyeball, give or take, that's about 100 million per second of going through your eyeball and your whole body. So we're talking, hundreds of billions. And you've never felt that wind blowing through.
Unlike when we feel that when we stick a hand out of the car in the example we gave, we feel that.
We do feel that. Yeah.
So it must be pretty fucking small.
Yeah, well, it's the fact that it's dark. So it's because it doesn't interact with light. So we call it dark matter because we know that there's something out there in the universe, huge amounts of gravity, right? We can see the motion, things are getting whizzed around, pulled by this stuff that is clearly there, but our telescopes can't pick it up in any wavelength of light. So it's not shining or absorbing light. So that's the dark bit of the dark matter. Because it doesn't interact with light, it means that even solid materials appear effectively like empty space. And that's because that picture of the atom we always have in our minds, where there's there's the nucleus and there's the electron whizzing around. The idea of that representing solid space, it's a nice picture, but the vast extent of the atom itself is this cloud of the electron that's around. And whenever you bring atoms together, and even right now, right, I'm going to touch a table and it feels like I'm touching that table. It's the atoms of my finger coming close to the atoms of the table. Light is exchanged between, it's virtual photons, but anyways, but the idea is there's an interaction. which the atoms of the table push back on the atoms of my hand, and I feel that there's a solid material there. But if you don't know about light, right, if you're the dark matter, then all of that cloud of electron, all of those pushing back, it just all disappears. It just doesn't affect you at all. In other words, the picture of the atom, instead of being this, big extended cloud of an electron that is a real big, solid obstacle to you, it just vanishes.
But does dark matter have energy?
It has energy, and if by just sheer chance, incredibly unlikely because it's so small, if it hits the nucleus, the center of the atom, it'll know about that because it's got mass energy as well. So you're going to get a collision like a snooker ball.
Right.
So you're going to have a head-on collision. Dark matter is going to come in, smack the center of the atom, and cause it to fly off. And that must be happening to us right now, right? There must be, every day you're going to have a few of your atoms of your body knocked flying by this wind that's traveled through you. You'll not notice that. Every time you sip a glass of water, you're drinking in 100 billion new atoms. So it's never going to be a noticeable effect. But that's why we built a better detector than the human body, which is the SABRE detector. So there is a 10-ton vessel sitting in my lab space at One Turner campus in Swinburne. We're a few months from taking that to an underground physics laboratory. So there is a cathedral-sized structure we've excavated at the bottom of an active gold mine, a kilometer under the earth in the town of Stoll in Victoria. A project led again by Elizabeth Ribeiro. And there we will place this dark matter detector. And what we're looking for then is that this dark matter is going to come flying through. Every now and again, it will hit the detector, which will glow. And the idea, very simply, is that we are looking to see, is it glowing basically from these collisions by a ghost?
And when you say glow, I mean, we're not talking about glowing.
Tiny little flashlight. Yeah.
So, but you have something to detect that sense.
Very, very sensitive cameras called PMTs. Yep.
Has this happened anywhere else in the world? I mean,
yeah, we are intentionally emulating a detector that was done in Italy, known as Dama Libre. So they have claimed that they've seen the dark matter detection. And in fact, there was a recent conference my student Grace Lawrence was at, and they once again reaffirmed this. 10 years now they've been saying they've seen this. They are definitively saying they've seen dark matter, and no one else, with all the other kinds of experiments, can see that signal. So we're all getting a little bit confused now as to what's going on.
Using the same detector?
No, that's the key.
Right.
So everyone else has done a slightly different approach. So we've thought, okay, we've got to get this sorted once and for all. So we have come up with the same kind of detector, which on ours is called SABRE, and that is being placed, as I said, underground.
Why do you place it underground? What's the point of that? I mean, I know that they do this in CERN when they're trying to smash various particles together, but why are these things underground? Is there some sort of danger or?
No, it's because we've got, it's essentially so that the detectors aren't blinded. So we have radiation from space constantly raining down on us. It's called cosmic rays. Even the sun itself puts out some of this, but mostly it's exploding stars, feeding black holes, you name it. Most high energy kinds of things in the whole universe constantly raining down on us right now. In fact, in our body, there's at least a few hundred of these hitting us every second. And they actually leave some impacts on your DNA, by the way, which is not an unappreciable amount of damage that eventually mostly gets fixed, sometimes doesn't. Now, those cosmic rays would blind our detector. It would definitely flash light when struck by this. I mean, it would be absolutely blindingly bright. So we have to take it a kilometer underground, use a kilometer of rock to block those cosmic rays. The dark matter is a ghost, just goes straight through that rock, and we hope very rarely, not too rarely, will hit our detector.
So you're going to bury it in the gold mine,
basically,
the old gold mine.
Yeah. But it's a very nice place to bury it. I mean, this is a really schmick-looking lab. This will be one of the cleanest sites in the whole Southern Hemisphere. It's going to be pristine. You go through. To get this lab is quite an extraordinary experience, but you literally get your high vis on, your hard hat, feel like you got a proper job for a second, and then you get in the truck and they drive you down the tiniest tunnel you've ever seen, and then these huge these huge trucks loaded with ore coming up and down.
Oh, so it's an operational.
It's an operational mine. Yeah. So you're sitting on this slow incline. You'll drive about 20 kilometers around to get 1 kilometer down. And all the while it's dark, you've got your lights flashing on the warning lights flashing on the truck cab, and it's getting hotter and hotter. Humidity's going through the roof, and eventually you turn off from this really constricted tunnel, and there is a ginormous door in front of you, and there's a little, essentially a shower that you have to take, get rid of all the dust, put your white lab coat on, and there on the other side of that door is this 12-meter high cathedral, high, internal.
It's like a movie.
High. It is like a Bond layer thing. It's incredible. It's incredible.
And are people working down there?
Yeah,
there's lab people down there.
Yeah. We're at 1 week. Yeah, so it'll be next week that we'll be opening the lab with all the media appearing. Everyone else.
That's really cool.
That's fun. Yeah.
And this is Swinburne. This is Swinburne's initiative, or is this Melbourne?
No. We're just one part. We're one part. So there's University of Melbourne, ANSTO, ANU. Princeton's been involved. I'm trying to think all of the other. I mean, just a huge collaboration. So some of the best unis in the world have gotten together to make this possible. Funded in part by the Australian Research Council. So it's a massive Australian effort to make this possible.
Okay, so let's say you get woken up at 2:00 in the morning in a year or two's time, and someone says, "Oh, we got the globe," and you're going to be all excited. What then?
Well, then we immediately go and ask for more money to build a bigger detector, right? I mean, what always happens with science is you need more data. I need more data. I think
what are you trying to find out though? What effect on humanity will it have, or is it just like the Finn story? And I don't mean this in a bad way, but there are other steps, and there's Finn, and it's a great story, and we live with that for the rest of our lives. That story, or is this going to have some effect on us? Change something about the way we live, or increase the standard of living? What will it do?
So the discovery of dark matter is going to tell us where to take modern physics. So we've basically, since the discovery of the Higgs boson, the God particle, some 10 years ago now, physics has been complete in as much as we've finished the standard model jigsaw piece puzzle for particle physics. Although we know that there's dark matter out there and it's unexplained in that model. We've got the theories of general relativity and quantum mechanics that don't integrate, they don't play well together. But we don't know how or what direction to take science to unify those, to gain that deeper understanding of the universe. So by discovering dark matter, it gives us a direction to take modern physics. And if we think back to what we've gained from these breakthroughs in understanding of nature, general relativity gives us GPS satellites, right? So I took an Uber here today. Impossible without GPS, which is impossible without GR. In the same way, we have modern computing that's only possible because of our understanding quantum mechanics. And again, that was an annoying detail about some kind of weird particle, and it wasn't, they couldn't quite understand why it was behaving the way it was. And then unlocks, actually Einstein as well, unlocks quantum mechanics. So in the same way, what we're hoping to do is by discovering dark matter, directing us to this next bigger theory that will unlock a lot of benefit. So that's the long-term view. Short term, the technology we create in those detectors has immediate spin out. So in fact, actually one of the kinds of ways to find dark matter, super light version called axions, that was undertaken by Mike Tobar in UWA. And his experiment just happens to be a super upgrade to airport radar landing system. The connections are absurd and incredibly surprising sometimes, but the way in which he was searching for dark matter is perfected the control of radio waves in exactly a way that airports wanted to have, and they get 100 times better, basically, performance. So the benefits for humanity in these cannot be easily foreseen. But the one thing we can foresee is that there will be benefits.
Well, I guess what you're saying is science has made these discoveries over the years, and over time they've been put into applications that actually help us live a better life, or maybe a safer life, or a more efficient life, or a longer life perhaps, or right down to things like MRI machines and all those sorts of, all the technologies that the medical practitioners use today. All of that stuff comes out of physics at the end of the day. All those capabilities come out of physics theories that exist within physics.
Yeah. And look, I mean, we take for granted Wi-Fi, but the underpinning technology and Wi-Fi is a spin out from the CSIRO's work looking for exploding black holes. Right? I mean, it's too hard to choose fundamental science directions, knowing what technology will come from it and how that can help and impact humanity. All we know is if you don't do the fundamental science and search, you won't have that pipeline of technology to translate into the real world. And I've lived this experience myself. So one of the spin-outs from our dark matter research, I've taken into a company called MDetect. Those cosmic rays I mentioned, those impacts, they are, because they shine through material, you can use them to take an X-ray of that material. So we came up with some very cheap commodity-based detectors for those cosmic rays. So right now we're actually on site in a few mine sites, and we're trying to scan their tailings storage facilities. These are huge structures where they put the waste from the mine site. And we want to make sure that those walls are nice and structurally sound. They're so large, there's no way to look through them. You can't scan them in any meaningful way, except you've got these particles from space that are crashing through all the time. So we put a detector between the wall and the sky, and we're using these cosmic rays to take an X-ray scan on the wall and say, yep, there's no cracks in that wall. There's no way I would have started a career in dark matter research thinking, I'll do this so I can help ensure there's not environmental disasters from spillages from mine sites, right? I mean, there's just no way to have done that direction. But so long as you're willing to be curious, and your university, as in my case, Swinburne, has been supportive of your ability to then go off and say, look, I think there's something could be interesting here. Maybe we'll take a quick diversion of the research, and I'll just take a quick look at this application, and then, spin out, and investment happens, and it's all been very positive. But there's no way to plan for these things. You can prepare yourself for the opportunity. You can be open to opportunities, but you can't predict those kinds of things happening. But that to me has been the beauty of research, the flexibility, the ability to follow an idea to either the research paper or to the VC round, whatever it might be. Is something that's very special in research, where you are entrusted, often in times with public funds. People trust you to go off to have a good idea, and that you're going to make good use of their investment in your time to discover something or to translate something. It's an incredible privilege.
And commercialization, which is what you're talking about now, of university, largely, a lot of times anyway, university engineered ideas into proof, which is what you do and what a lot of people do. The commercialization, to some extent, is a big driver of the growth of science for people to study in the future, because science was a bit of a left behind discipline. Because I remember when I was at university, no one went to university to do science. You might go and do engineering, but you didn't do science, because science wasn't considered, you can't make any money. And why would you want to become a scientist? I'm going back 45 years. Even more, actually. So everybody did humanities, become a lawyer or doctors were one, but doctors weren't really coming out as scientists, so more practitioners, clinical stuff. But science, but all of a sudden we had this thing, we need to have much more science. And of course, what's happened is that over the past maybe 10 years, science has become a big deal. And now we've got people like Richard Branson involved, Elon Musk, especially in space. Oh, yeah. Elon Musk, big time. What is the attraction for these individuals? What's the symbiotic sort of nature of them and scientists? I mean, are both parties equal in their objectives, or is one party just trying to make a discovery that they can turn into something like you just explained, some commercial application? Or do they have the same general curiosity that a scientist would ordinarily have?
Okay.
But how does that all work now? Because it's a big deal now. Musk has done two things. He's made the brain really important with Neuralink.
Oh yeah.
We talk about space. If space is out there, it's so big, it's ridiculous. It's bigger than anything. But then we forget about the brain. So Musk has done two things. He's gone to the brain with Neuralink, and he's gone to space.
Yep.
And he's nailed both of them. I'm not saying he's discovered anything, but he's nailed both of them. He's trying to nail both of them. Yep. Okay. And off the back of that, others have gone, hang on, we can do that. So now we've got Synchron, who's gone and copied what Musk is doing in Neuralink, but actually is ahead of him. And it's an Australian business, and they're doing even better. They're going at a fast speed. But if it hadn't been Musk, maybe no one else would have had the courage to go and do it, because they thought, shit, we won't be able to track the money.
Yep.
These things need money. to pay for everybody. You've got to get paid. And universities can't do everything. They're constrained. The government doesn't put the money in university pay for your discoveries. You have to get grants.
Oh, yeah.
And you've got to go and get sponsors.
Basically,
you're finding sponsors all the time, and a lot of times they're external.
Absolutely,
when I say external, they're commercial businesses. People say, "Hang on, this guy, we might just follow what Alan's doing because this could be quite good.
Yeah,
there could be something in it for us." So there's a misconception the government's pouring money into these things. It's not government. Sometimes they do, but a lot of times
it's definitely not only government. Yeah, so
externals, right? You have to get patrons or sponsors and stuff like that. So how important is that new phenomenon that exists today, and how important is people like Musk, who's got ridiculous following and cut through? How important is that to continue to develop science?
Oh, it's huge. Sorry. So we have, God, there's so much to unpack there. So I'll just finish that point about the our search for external sponsors. So I had the Space Technology Industry Institute at Swinburne, and that is externally focused. So yes, there's research grants from government. Most is actually from industry. And it's industry who knows that they need to innovate to still be alive tomorrow, right? They've got to be at the cutting edge of technology. And often that technology, those solutions are sitting in a lab bench in the uni. So now we've got to take that and bring it into the marketplace. And that's a really hard path, really hard path. It's not clear the scientists are the ones who should be doing that, by the way. And I think there's some scientists like myself who like to give it a go. Most scientists are great at the research, and most entrepreneurs are great at taking that research and getting it to a market. And that's what Musk's genius is. Absolutely no doubt about it. And you've mentioned two of his breakthroughs, arguably the electrification of transport, so Tesla. In doing Tesla, his biggest impact was the fact he forced every other car manufacturer in the world to also now offer electric vehicles.
True disruption.
Fast. So that's why I'm becoming optimistic with our climate change adaptation mitigation future. I think we'll get there eventually, but in part it will be because of those efforts to show that there's a technological solution that makes sense, that can save the planet. But you know what? It's actually desirable. Like, it's a better product than what came before. So that itself is also a breakthrough. Now, that has a huge impact into the research landscape. It has an impact into scientists worldwide, because now there is a tremendous amount of government and in particular private investment into new kinds of batteries, new kinds of technology, lighter weight materials, bring down the weight of that vehicle, and you can let it drive longer on the same charge. So you can see all of these huge advances occurring, and young people find that this is now an attractive career path. This is cool. You're saving the world. You're inventing great technologies. So I think that it has raised the cool factor of science. I think SpaceX in particular, what it's done for drastically lowering the cost of access to space. The concept is just so profoundly simple, but so disruptive for that. The idea being traditional rocketry, launch the rocket, one of the marvels of engineering, and it just tumbles back to Earth. And as we've seen, literally just the last few weeks, pieces are hitting Earth all the time. Musk's brilliance was, well, if I take a plane to an airport, I don't scrap the plane at the end, do I? Load passengers up, fly back. So reusability. Why are we not doing that in rocketry? Easy said, very hard to do. But SpaceX was able to perfect the technique of landing their own rockets. And now suddenly you haven't just done a launch with a $10 million asset. You've recovered that $10 million asset, fix it, costs a little bit of money, but now it's drastically.
Also not scrapping everything. Yeah. Or stuff's not floating around in space.
Yeah. Oh, it's environmentally, it's much a better solution as well for that reason as well. So now we've got access to space. Elon Musk has drastically reduced the cost of space. Swinburne, we have a program where high school students can design, build, literally manufacture an experiment, and we'll take it to the International Space Station on a SpaceX rocket. And after a month on the space station, it will be returned to them. And the most recent examples of space yogurt. So the students thought, well, we're going to be going to Mars. There's these, year-long trips. The astronauts are going to want fresh produce. So, let's look at yogurt. But how is the microgravity conditions, radiation of space, how's that going to affect the bacteria that grow, that make the yogurt? So they wanted to see, would space yogurt be tasty still? Now, that right there encapsulates the creativity and brilliance of a young mind. To even think of that experiment, I certainly hadn't. They worked for 3 months all through their break. They created the experiment. We launched it in the last campaign. It's now been safely recovered a couple of months ago from the International Space Station.
How'd it taste?
Well, we haven't grown that yet. So I've just realized there's probably some serious OHS issues that I need to try to grapple with at this point. Paperwork may get in the way, but I think we will actually be growing those and tasting it soon. But the idea, at least from the student, like we are literally going to grow, make the yogurt, and then we'll have to do some actual proper chemical analysis just to check nothing's changed in the production of the yogurt. But the idea is that because Elon Musk was able to reduce the cost of access to space through that technological innovation, I and my colleagues, Rebecca Allen and Sarah Webb, have been able to provide students, high school students, access to the space station. That's, how disruptive
so
is that?
Cool, man.
Yeah, and how inspiring is that?
Yeah, that's so cool. And shit like that never happened when I went to school. But like, it's so cool. But I just want to ask you. I think this is really important to me. So there's a book that you guys are launching. What do we got here?
So this is for the Melbourne Writers Festival.
Yep.
It's a book written by Carly Noon and Crystal DiNapoli, to astronomers, to Indigenous astronomers here in Australia. And it's called First Knowledge's Astronomy. And it is about the incredible understanding and detailed knowledge of the sky that the Indigenous peoples of Australia had. It just makes such a compelling case for how advanced that understanding was of the night sky. It's an incredible read, but we'll be speaking, I'll be interviewing as part of the Melbourne Writers Festival to explore some of those concepts, but in particular, that detailed understanding of the night sky
by the Indigenous
people.
Yep.
We're talking 30,000 years ago, long before the pyramids. You have Indigenous peoples here in Australia understanding the connections between the moon and the tides, being able to predict the tide based on the feature of the moon, being able to forecast weather days in advance, being able to time their hunting for the eggs of the emu based on the visible extent of the Milky Way galaxy, and all the while, all the stories that they have captured around the visible changes of the night sky, noticed over years these patterns, and then faithfully told through countless generations, through story.
You're not written, by the way, told.
So absolutely perfect oral translation and memorization. And that's the power of storytelling, right? It's hard to memorize facts. It's very easy to remember story. That's just the way our brains are. So they were able to impart detailed knowledge about the land, the connection between sky and country, detailed knowledge about rules of their people, what is, totemic animals, what's sacred law, so much incredible wisdom associated with it. And modern science, astronomy in particular, is only now just beginning to recognize how detailed and accurate the measurements, again, all by eye as well, of the night sky has been. There's one particular story where they describe the ability to discern that stars change in color and brightness over the course of years in a sequence that's about 20 to 30 years long. So someone has remembered by eye, and there's nothing able to now.
Through observation, it's amazing.
This has changed over decades, been able to create a story that describes that, predicts it, and pass that on. And then 10,000 years later, we're sitting with the book.
It's taken they've done it over 30,000 or 40,000 years, which is probably one of the arguments why we need supercomputers, or maybe even quantum computing, to help us get it done much quicker, because you and I don't have that time.
No,
that much.
We've definitely run out of time.
So we're going to Science Week. You're going to the Writers Festival and launch this particular book.
Yes, on behalf of with Carly and Crystal. Yep.
And that's on the 11th of September.
Yep.
What do you want to say to us just to close off?
All right. Well, look, I'm doing a science to science fiction talk on the 15th, which I think beautifully encapsulates it. Science Week is about making science relevant and engaging and reminding everyone how part of our everyday life it is. I'm doing that through the use of Hollywood. Some colleagues are doing use of demos. There is just on the scienceweek.net.au website that you will see thousands of events across the country where scientists are out of the lab. They're trying to get into in front of you and explain to you just how exciting and fun science and a career in science is. It's not the dry analytical perception we started with. It is creative, it is fun, and it is innovative. And that's a wonderful place to be.
I love the whole sense of imagination. I love how you started this off talking about the idea and the science but the imagination that the Irish held, then brought it straight back to, our Aboriginal our Indigenous brothers here in Australia, how they used their power of observation, but passed it on through stories, through generations, thousands of generations. And I loved everything that sat in between. So, Professor Alan Duffy, thanks very much.
Thanks so much, Mark.